Welcome to this explainer. Okay, today we are diving into something absolutely massive. We are unpacking a fundamental problem in mathematics and a truly revolutionary architectural fix, Peter Scholze's lectures on condensed mathematics. This framework fundamentally reconstructs how we view space and structure, and we are going to break down exactly how it works. It's an epic journey, so let's get into it.
So here is the inciting incident, the million-dollar question we're dealing with right off the bat. How on earth do you do algebra when your rings, modules, or groups actually carry a topology? Think about it. How can we possibly mix the strict, discrete, unbending laws of algebra with the continuous, squishy, messy shapes of topology? Historically, trying to force these two totally different worlds together has just caused mathematical systems to break down completely.
To wrap our heads around Scholze's brilliant solution, here is our cognitive roadmap. First, the topological algebra problem. Second, enter condensed mathematics. Third, translating through profinite sets. Fourth, the magic of solidification. And finally, a new mathematical architecture.
Let's start with Section 1, the topological algebra problem. Getting algebraic exactness to play nicely with topological fluidity has been a historical nightmare. It's literally like trying to mix oil and water. On one hand, you have the cold, rigid, unassailable certainty of discrete algebra. On the other hand, you have the sprawling, transfinite, fluid nature of topology. The standard rules of topology simply let way too much messiness through, which results in what mathematicians call pathological errors. Basically, things that just shouldn't happen but somehow do.
The issue is that when you try to stretch discrete, finite rules over infinite, complex spaces, the math just snaps. Relying solely on a finite, discrete baseline, like your standard, everyday natural numbers, leaves the whole mathematical system incredibly fragile. It simply cannot scale up to handle transfinite complexities without catastrophically breaking its own rules.
Which brings us to Section 2, enter condensed mathematics.
So Peter Scholze steps in and completely bypasses this fragility with something called a condensed set. Now, the highly technical definition is a sheaf of sets on the proadal site of a point. But what does that actually mean for us? Well, it means we are completely throwing out standard topological spaces. We're abandoning them. Instead of using traditional open shapes to measure space, Scholze's framework uses highly structured, extremely disconnected dots, these are called profinite sets, to rigorously test and evaluate how spaces interact. Let's look closer at how that works in Section 3, translating through profinite sets. Think of this exact pipeline almost like a giant water filter. Your input is the messy, continuous, traditional topological spaces. The mechanism, the filter itself, is made up of profinite sets and extremely disconnected spaces. And what comes out the other side? Your output is a condensed set, perfectly structured algebraic objects that hold on to all that important topological information, but without any of those messy pathological errors. It's completely cleaned up. Now, what's really fascinating about this translation mechanism is the stone check compactification. This essentially takes our standard finite numbers and packs them into an incredibly dense mathematical space where every single possible infinite limit is captured. It acts as the ultimate transfinite extension of our finite numbers. It's a fail-safe ensuring absolutely nothing slips through the cracks. In fact, the sources literally describe these structures as the ultimate transfinite extension, an invisible constitution. I mean, an invisible constitution. How powerful is that? This isn't just some clever mathematical trick. It's a profound structural blueprint for how continuous space actually behaves at its deepest, most fundamental level, systematically organizing transfinite data to keep the whole system perfectly stable.
Now for the really cool part, Section 4. The magic of solidification. Scholze builds this up into a climactic resolution that breaks down into a really straightforward, digestible pipeline. Step 1. You start with your ordinary, unstable topological modules. Step 2. You apply z-measures, which basically evaluates these spaces through the strict lens of those extremely disconnected sets we just talked about. And Step 3. You transform them into solid abelian groups. You are quite literally solidifying the messy topology into something perfect. And Theorem 5.8 is where we get the proof of why this new category is an absolute game changer. It provides unassailable stability.
These new solid abelian groups form a flawless, perfectly stable subcategory. They literally do not break down, no matter how much you stretch them through limits, colimits, or extensions. By using compact projective generators as a basis, this solidification process takes the sheer vastness of the infinite and locks it down into a structurally perfect framework.
Let's zoom out for Section 5, a new mathematical architecture.
We start this new reality right at the absolute baseline, 0, the empty set. But here, it isn't exactly just nothingness. It acts as an active, unconditioned interface. It's the miraculous assembly of substance from nothing, the absolute baseline required before any mathematical judgments can even be made.
And then, instantly contrasting that 0, we jump straight to infinity. The condensed mathematics framework scales all the way up to ultra-filter dynamics, where infinite subsets are judged with merciless, binary finality. In this transfinite realm, there are absolutely no gray areas. Every single piece of topological data is rigorously sorted. You are either perfectly inside the structure or you are outside of it.
Because of this, the Boolean algebra of the power set maps directly, perfectly, one-to-one to the points within the compactified space. It means every single sequence of mathematically sound decisions converges perfectly in this transfinite remainder. It's this beautiful, invisible architecture where nothing is ever lost and absolutely nothing breaks down.
So, what does this all mean? When we look at how elegantly Peter Scholz's lectures on condensed mathematics resolves the deepest, most stubborn conflicts between algebra and topology, it leaves us with a truly profound thought. Are mathematical laws merely human inventions, just tools we made up? Or are we actually discovering the inevitable, foundational topological blueprints of reality itself? Thank you so much for joining me on this explainer. I hope this sparked your curiosity to look even deeper into the invisible architecture that surrounds us all.